Welcome to the deep dive. Today, we're jumping into a topic that, well, it might not sound thrilling at first, but it's really vital for keeping so much of our technology running properly.
Yeah, absolutely.
We're talking about preventing carbonate scaling in water heat exchange systems.
hmm
Think about anything that heats or cools water. Could be the system in your office building, could be huge industrial cooling towers. You get the picture. This scaling stuff affects efficiency, how long things last.
It really does. And the insights we're diving into today, they largely come from some really thorough research by Serhiy Andriyovych Kontsevoy, specifically his dissertation from back in 2011.
Right. So think of this as your, let's say, express lane to understanding the heart of his work. We're aiming to pull out the key stuff without you getting totally bogged down in, all the dense scientific detail.
That's the plan. Make it clear, make it engaging, even if it sounds a bit technical on the surface.
So what was Kontsevoy really focused on? What's the core problem here?
It really boils down to how the dissolved stuff in water, how it behaves when you heat that water up.
Okay.
It's not just about the heat, it's how that hot water interacts with the surfaces.
Yeah.
It touches the pipes, the exchangers, the whole system, really.
And that interaction causes buildup, scale.
Exactly, scaling. And it's not just, unsightly. It makes the system work harder, use more fuel or energy, and it can even cause failures because of corrosion hidden underneath.
And I gather this isn't exactly a new headache. The research mentions issues with older standards.
Oh, definitely not new. He points out that in many places, particularly former Soviet countries like Ukraine, the existing standards for water treatment in heating networks, well, they were often based on old Soviet norms.
And those norms weren't always great.
They often led to problems, yeah. Especially things like internal corrosion, which was apparently a big issue in southern and eastern Ukraine.
Okay. And Kontsevoy's work looked at different kinds of systems, right? Not just heating.
Correct. He looked at two main types. The big heating supply networks, what we call thermal networks.
Right. District heating, that kind of thing.
Exactly. And also cooling systems. And what's interesting is that the ideal water chemistry, specifically the pH level, is different for them.
Absolutely.
Generally, for heating networks, they aim for a pH above 8.3. But for cooling systems, it's usually kept below 8.3.
Huh. Different targets. So what was the big unanswered question, the sort of roadblock Kontsevoy was trying to get past with his research?
The main hurdle, really, was the lack of a good, scientifically sound, fast way to predict if a certain water type would form calcium carbonate scale when heated to a specific temperature.
What were they doing instead?
The existing methods often involve these lengthy simulations, almost like building a mini version of the real system. And these could take weeks, sometimes even months, just to see a scale would form.
Weeks or months just to get a yes or no on scaling. That sounds incredibly inefficient.
Totally. Imagine trying to optimize a system or choose a water treatment if you have to wait that long for feedback.
So Kontsevoy's primary goal was to speed that whole process up, find a shortcut.
Essentially, yes. His core objective was twofold. First, to develop the underlying theory, and second, to create a practical lab method, a way to quickly test a water sample and predict its tendency to form scale.
And based on that, you could then figure out the best way to use that water in heating or cooling systems.
Precisely. Define the conditions where it's safe and efficient.
Makes perfect sense. So where did he start? How do you even begin to unravel that?
Well, he started by really digging into the existing understanding of how calcium carbonate forms in heated water, particularly when there's no air contact.
Why is the no air contact part important?
Because the chemistry changes quite a bit when oxygen and CO2 from the air can get involved. Many heat exchangers are closed systems, so that no air condition is actually more relevant.
Okay. And what did he find when he looked at those existing theories? Were they holding up?
He found some pretty significant gaps, limitations in how people were evaluating this potential for carbonate scaling, the Russians call it S. The models just weren't always predicting accurately what happened in real systems with different water compositions.
So the existing tools weren't quite sharp enough. A rethink was needed.
Definitely. Which leads us to his revised look at carbon dioxide equilibrium in water.
Ah, the fundamental chemistry. What was his new take?
He proposed that within the typical pH range you find in these systems, say pH 4 to 11, it's more accurate to think about the carbonic acid equilibrium as really being a bicarbonate equilibrium.
Bicarbonate equilibrium. Okay, unpack that a bit. What's the key difference?
The main idea is that bicarbonate ions, that's HCO3, don't just break down in one single way when heated. He suggested there are actually two main mechanisms, and the water's pH decides which one dominates.
Two paths, depending on pH.
Yeah. Below a pH of about 8.35, he proposed what he called the OH mechanism. Here, the bicarbonate ion basically reacts with hydroxide ions, the OH, to form water and carbon dioxide gas, CO2.
Okay, that's one way. What happens if the pH is higher than 8.35?
Then, according to his theory, the H plus mechanism takes over. In this case, the bicarbonate ion acts more like an acid and splits into a hydrogen ion, H plus, and a carbonate ion, CO3d2. And that carbonate ion is the key ingredient for forming calcium carbonate scale.
Wow, okay, so the pH is like a switch, flipping the bicarbonate between two different behaviors. That sounds quite different from the standard textbook explanation.
It is. The common reaction you often see used, especially for water heated in contact with air, involves two bicarbonate ions reacting to form water, carbonate, and CO2.
Right, I think I remember that one.
But Kontsevoy argued that the equation has real problems, especially in closed systems. It doesn't correctly predict, for example, how the amounts of carbonate and dissolved CO2 should relate to each other at different pH values. It sort of averages things out in a way that misses the mark.
So the big insight is that bicarbonate is more flexible. It can act as a base or an acid depending on the pH environment.
Exactly. And based on this, he actually derived a new dissociation constant, specifically for that OH mechanism, the one dominant at lower pH. He called it K2.
Another constant. How does it help?
Well, he showed that using this new constant, or even the standard first dissociation constant for carbonic acid, K1, gives you pretty similar and more accurate results when calculating the concentrations of dissolved CO2 and bicarbonate at a given pH compared to the old way.
Okay, so it offers a more refined calculation. But how did his new constant K2 compare to existing values in the chemistry literature?
That was a really key finding. He compared it to the standard hydrolysis constant for bicarbonate you'd find in textbooks, often written as K2 divided by K1. And his K1 was significantly larger, like by about 3 orders of magnitude.
1,000 times larger. Whoa.
Yeah, it's not a trivial difference. It suggests a fundamental shift in how we should be modeling these equilibria.
Okay, that is a big deal. How did he actually go about proving these two different mechanisms, the OH and H++, were real, experimentally?
He devised a rather clever lab setup using simplified water solutions. He'd mix solutions of calcium chloride and sodium bicarbonate that had the exact same initial pH and concentration.
Without heating them.
Right, without heating. And he'd very carefully measure the pH change immediately upon mixing.
And that pH change was the clue.
Precisely. If the pH went up slightly, it indicated the OH mechanism was dominant. If it went down, the H plus mechanism was the main player.
Neat. A direct test.
And this led him to define a specific pH value, which he called pHa, pH delta. That's the point where the mechanism switches over. He found this pH wasn't fixed. It actually varied depending on the water's hardness and alkalinity.
Which makes sense. Those affect the water's chemistry. What range did he find for this switch point?
It typically fell between about 7.25 and 8.30 in his tests.
Okay. Did anything else influence it?
Yes. He also tested adding a complexing agent, Trilon B, which is sometimes used as a scale inhibitor.
And what did that do?
It actually shifted the pH upwards quite noticeably, from around 7.6 up to 9.0 in one case. This shows that adding certain chemicals can actively push the equilibrium towards one mechanism or the other.
Fascinating. So these mechanisms aren't just theoretical, they explain real chemical behavior.
Absolutely. Kontsevoy used them to explain phenomena like why the pH goes up when sodium bicarbonate decomposes and releases CO2 that fits the OH mechanism becoming dominant, or the pH shifts you see during deep water softening in ion exchange filters.
And how does it connect directly to the scale forming?
Well, he showed that the H plus mechanism, the one that produces the carbonate ions needed for scale, actually causes the pH to decrease slightly, even before any solid scale precipitates out.
So the pH drops before you see scale.
Yeah. And conversely, if calcium carbonate scale starts to dissolve, the pH goes up because the H mechanism is now working in reverse, consuming H plus to form bicarbonate. It gives a much clearer picture of the pH dynamics during scaling and dissolution.
Okay, this revised understanding of bicarbonate seems absolutely central. Let's shift to the practical side, the experimental method he developed to actually measure this scaling potential,
Right, this was a major practical contribution. He designed a lab test specifically to mimic what happens inside a heat exchanger heating water without it being exposed to air.
A closed system test. How did it work?
Pretty straightforward, actually. He'd take water samples, thermostat them, measure the starting pH, let's call it pH 1.
Okay.
Then he sealed the samples in stainless steel reactors, heated them to a set temperature anywhere from 40 degrees C up to 190 degrees C for 30 minutes.
Why 30 minutes?
He found that was generally long enough to represent the heating effect in many real-world systems. After heating, he'd cool the samples down and measure the final pH, pH 2.
And the key is the difference between pH 1 and pH 2.
Exactly. He defined his experimental measure of scaling potential, air, as simply pH 1 minus the average final pH.
So initial minus final. What did the result tell him?
He found a really useful correlation. The sign of this Aya lined up well with the predictions of the older Langelier saturation index, at least up to about 90 degrees C, where Langelier is reliable.
Oh, so?
A negative UR, meaning the pH went up after heating, indicated that carbonate ions weren't forming significantly. That corresponds to his OH mechanism being dominant.
Okay, negative is good, no scale risk.
Right. But a positive UR, meaning the pH dropped after heating, indicated that carbonate ions were forming via the H+ mechanism, suggesting a potential for calcium carbonate scale to precipitate.
So a simple pH test before and after heating in a sealed tube gives you a direct indicator of scaling risk. That's much faster than weeks.
Much, much faster.
Yeah.
And he validated it by testing waters with known scaling tendencies. His results matched expectations. Waters known to cause scale gave positive URA. Non-scaling waters gave negative UR.
That's crucial validation. Did he explore how things like hardness and alkalinity affected this UR value?
Yes, systematically. For the temperature range relevant to cooling systems, say 40-80 degrees C, he found that typical industrial waters meeting standard norms, like pH 6.5, 8.5, consistently gave negative Vis values.
So the standard seemed okay for cooling systems according to his test. What about higher temperatures, like in heating networks?
At 150 degrees C, typical for thermal networks, the picture was more mixed. He saw both positive and negative UR values depending on the exact water chemistry.
Ah, so higher risk there.
Potentially, yes. But importantly, he identified specific conditions, certain ranges of hardness and alkalinity, combined with an initial pH below 8.3, where the UR remained negative even at 150 degrees C.
That's really valuable. It suggests you can prevent scale even at high temperatures if you control the water chemistry precisely using these parameters.
Exactly. It opens the door to optimizing treatment. Interestingly, he also tested water based on German thermal network standards at 150 degrees C. That water, despite having much lower hardness than typical Ukrainian network water at the time, actually showed a positive hit.
So even low hardness doesn't guarantee no scaling risk at high temperatures if the other factors aren't right.
Apparently not, according to his method. It really highlights the interplay between hardness, alkalinity, pH, and temperature.
Did he try to capture these relationships in, like, predictive formulas?
He did. He developed both simpler linear equations and more complex quadratic ones to estimate a WA based on hardness, alkalinity, and initial pH for different temperatures. And he stressed that these formulas were much more accurate because they implicitly accounted for which bicarbonate decomposition mechanism was likely dominant.
Right, building the mechanism into the math, not just curve fitting. Makes sense.
He also introduced another useful concept, the conditional saturation temperature, or the
Conditional saturation temperature. What's that?
basically the calculated temperature at which his value would be exactly 0. He linked this to the temperature where the water becomes perfectly saturated with calcium carbonate, according to the Langelier index, the point where scale is just about to form.
So instead of just a positive or negative indicator, you get an actual temperature threshold.
Yes, a temperature below which you're likely safe, and above which the risk increases. For example, using his linear formula for Kyiv tap water, he calculated this T to be 86 degrees C.
That's a practical number. You know, if your system runs hotter than 86 degrees C, you need to be careful with that water.
Precisely. And he also noted that at 190 degrees C, the IR for that same water was significantly positive, showing the much higher risk at very high temperatures.
Okay. Now, earlier you mentioned he also measured hardness changes. How did that fit in?
That was an important addition to the method. He measured the hardness before heating and after heating and cooling. The difference he called IA.
Change in total hardness, essentially.
Right. And if the hardness decreased, meaning IA was positive, it's direct physical evidence that calcium ions have been pulled out of solution to form solid KCO3 scale.
So the pH change predicts the potential, and the hardness change confirms if scale actually formed in the test.
That's a good way to put it. It adds another layer of confirmation.
Did anything else affect these measurements, like how quickly you cooled the samples down?
Interestingly, yes. He found rapid cooling tended to lock in the conditions from the high temperature, often giving positive Yoch values if the H+ mechanism was active. But slow cooling sometimes resulted in negative Yoch values.
Why would slow cooling change the result?
He speculated that during slow cooling, the OH mechanism might become dominant again as the temperature drops, potentially consuming some of the CO2 produced by the H+ mechanism earlier, thus raising the final pH.
Huh. So the cooling rate itself matters. That's a subtle detail.
It shows how dynamic these equilibria are. He then linked the pH drop, positive Ur, from the H mechanism directly to the amount of H+ ions produced and how these react further. He even derived equations to calculate the change in carbonate concentration based on the measured pH change.
And did those calculations match the hardness drop he measured?
They correlated very well. He showed that the measured hardness drop typically accounted for about 74–85% of the H+ ions calculated from the pH drop. It provides strong evidence connecting the pH change directly to the amount of calcium precipitating out.
Okay, chemistry is tying together nicely. Now let's talk about this idea of admissible change. Adichem, you called it. What's the significance of that?
Right, idsdilem. This is Kontsevoy's concept for the maximum allowable pH drop, or minimum pH rise since it's usually negative, where scale formation is negligible.
Negligible meaning undetectable.
Essentially, yes. A point where the H mechanism might be producing a tiny trace of carbonate, but not enough to cause a measurable decrease in water hardness. So IDJA would be 0 or even slightly negative due to other effects. It's the threshold for practical scale prevention.
So if your measured is below this admissible value, you're in the clear.
That's the idea. To find this value, he did experiments mixing tap water with varying amounts of softened water.
Why softened water?
To systematically change the hardness while keeping other factors relatively stable. But he found something unexpected. In some mixes, especially those with more softened water, the hardness actually increased after heating.
Increase? How?
He theorized that the softening process itself creates some unstable calcium complexes. These don't react initially in the standard hardness test, but they break down upon heating, releasing calcium ions back into the water and making it seem harder.
Wow, so the initial hardness test might underestimate the total calcium available to cause problems later.
Exactly. A really important nuance. He even figured out how to calculate this theoretical hardness increase again, based on the amount of softened water used.
Okay, so accounting for that hidden hardness, how did that help find the admissible pH change?
By looking at the net hardness change and relating it to the pH change, he could pinpoint the condition where the net hardness change was 0. This occurred when his mind was about mecalo point 0.
So EDOM is roughly 0.10 mo, meaning the pH needs to rise by at least 0.1 units after heating to be considered safe from scaling.
Based on his experiments, yes, that became his condition. For effective scale prevention, the measured EDO should be less than, more negative, than this EDO of money of 0.10.
And could you use this to define a safe operating temperature?
Yes. By extrapolating the data showing how avidity changes with temperature, you could find the admissible water heating temperature, Teta, the temperature at which it would equal EDO Rome. For his Kyiv tap water example, this Teta was around 73 degrees C.
Below 73 degrees C. Okay, above that, scaling risk increases significantly based on this measure. That seems really practical. How did he suggest applying this in actual water treatment?
One key application is in figuring out the right dose for scale inhibitors, like that Trilon B complexing agent.
How would that work?
You'd use the EDOM threshold. The goal is to add just enough inhibitor so that when you run the experimental test measuring at EDOM, the result stays below Warabin.
So you're not necessarily removing the hardness, just preventing it from precipitating.
Exactly. And his test showed something remarkable. Often, only about 30% of the theoretically required amount of Trilon B was enough to keep SEA below the admissible level.
Only 30%. That could mean huge savings on chemicals.
Potentially, yes. It suggests you might be able to achieve good scale control much more efficiently than previously thought.
What other applications did he foresee?
He talked about the potential for zero discharge systems. Instead of softening water, which creates wastewater, you could use precise inhibitor dosing to allow higher operating temperatures without scale, thus reducing the need for blowdown or discharge.
Using less water and fewer chemicals, that's very relevant today.
Definitely. He also suggested that even the wastewater from reverse osmosis systems, the concentrate or retentate, might be usable as a heat transfer fluid in cooling systems if its admissible heating temperature, Tatamin, could be raised sufficiently using inhibitors or maybe some targeted ion exchange.
turning waste into a resource. Great potential there.
Okay, let's shift to applying this in operating thermal networks. How did the method adapt?
He modified the procedure slightly to account for the fact that water in a real network might already be preheated or have undergone some chemical changes. He then tested it in actual Kyiv heating networks, specifically under the high pH carbonate operating regime.
And what did these real-world tests show?
They confirmed his earlier lab finding that standard tests often underestimate the true hardness of water after sodium-cation exchange softening.
That hidden hardness again.
Yes, and also the impact of tiny suspended particles, colloids, on hardness measurements. Interestingly, he saw a larger increase in hardness after heating in one plant, ST1, compared to another, Darnitska Tech.
Why the difference?
He linked it to whether the initial river water treatment included coagulation, a process that removes those fine particles. ST1 didn't use coagulation for the makeup water going to the boilers, providing hot water for the city, while Darnitska did. It suggests those colloids released from the softening process really do play a role. So, the water plant's pre-treatment choices have downstream effects on scaling potential.
It appears so. He also analyzed why operators use that high pH carbonate regime, even knowing the KCO3 scaling risk.
Why do they?
The main reason is to try and reduce corrosion caused by iron oxides forming after the initial treatment, without having to add dedicated anti-corrosion chemicals. It's seen as a way to form a somewhat protective layer.
A trade-off, then. Less iron oxide corrosion, but more risk of carbonate scale.
Exactly. But this leads directly into the next big issue he tackled: oxygen corrosion.
The other major problem in these systems. What was his approach here?
He developed a method to calculate the actual average oxygen concentration in the network makeup water. This is tricky because you often have untreated water leaking into the system, say from faulty heat exchangers in buildings.
Leaks bringing in fresh, oxygenated water.
Precisely. His calculation method accounted for the flow rate of this leakage water mixing with the treated, supposedly deoxygenated water from the plant. Using typical Kyiv water data, his calculations showed these leaks could easily raise the average oxygen level far above the permissible limits, even if the water leaving the plant was okay.
So the carbonate regime isn't really solving the oxygen problem caused by leaks?
Not effectively, no. He analyzed the efficiency of the protective film formed under this high pH regime. He calculated a metric called the degree of corrosive oxygen reduction.
And how effective was the film?
Pretty poor, actually. Often less than 10% effective at preventing oxygen corrosion.
Less than 10%, that's hardly protective.
Worse, he argued, this patchy film could actually promote pitting corrosion localized deep attack because it reduces the total surface area exposed to oxygen, concentrating the attack on small, unprotected spots.
So the protection could make things worse in specific areas. Ouch. What's the alternative then, especially if you wanted to use the lower pH carbon dioxide regime to stop carbonate scale?
He stressed that effective oxygen corrosion control is absolutely essential if you want to run at a lower pH. You have to prevent widespread oxygen attack first.
Oh.
By selecting the right anti-corrosion treatment, specifically oxygen scavengers like sodium sulfite, and dosing them correctly based on the actual oxygen level, including the leakage.
Okay.
And critically, he highlighted the need for a catalyst, like cobalt nitrate, when using sodium sulfite. Without the catalyst, the reaction to remove oxygen can be too slow, especially if there's an excess of sulfite for other reasons.
A catalyst is needed to make the scavenger work properly. Did he see proof of that?
Yes, he observed rust forming in experiments even with plenty of sodium sulfite present. Adding the catalyst stopped the rust. He also estimated the cost of this sulfitation treatment would be relatively low.
So managing oxygen corrosion is key to unlocking the benefits of the lower pH regime for scale control. Makes sense. Let's cover the last main area, cooling systems. How did his work apply there?
For cooling systems, the focus shifts slightly. He developed calculation methods to understand the composition of the water as it circulates and evaporates, concentrating the minerals.
Right, because cooling towers evaporate a lot of water.
Exactly. This helps determine the necessary blowdown rate, how much concentrated water you need to drain and replace with fresh water to prevent scale, particularly calcium sulfate scale, which is often the limiting factor in cooling systems because its solubility decreases as temperature increases.
So, managing concentration. How did his method improve on existing ways to calculate blowdown?
He introduced a concept called the evaporation coefficient, which relates the evaporation rate to the rate of water loss through drift, fine spray. Using mass balances, he derived equations for this coefficient and the resulting concentration factor, how many times more concentrated the circulating water is, than the makeup water. He even calculated the maximum possible concentration factor, SMAX, if you had zero blowdown.
Predicting the maximum concentration based on system physics.
Yes, based on actual system parameters, rather than just generic guidelines. He showed his method gave results consistent with older approaches, but allowed for more specific calculations based on real data.
Okay. And how does this help with preventing scale, like calcium sulfate?
He defined a maximum permissible concentration factor specifically for calcium sulfate, based on its solubility. If the calculated maximum concentration factor, SMAX, for your system is higher than this permissible limit, then you know you must implement forced blowdown to stay below the limit and prevent chaos over scale.
A clear criterion for when blowdown is essential for sulfate scale. What about carbonate scale in cooling systems?
He connected it back to his earlier work. He argued the target pH for the circulating water, often used to control automated blowdown systems, shouldn't just be an arbitrary number. It should be set based on the admissible pH con, determined by his ASO method for the specific water and operating temperature.
So use the SOL test to find ASIM for the cooling water and set the controller to maintain the pH at or below that level via blowdown.
Exactly. The relationship between hardness, alkalinity, and temperature would be determined beforehand and programmed into the controller.
A much more tailored approach to pH control. Did he mention acid dosing, which is common in cooling towers?
Yes. He noted that adding sulfuric acid lowers the pH, which increases the amount of calcium carbonate the water can hold, increases the admissible concentration factor for KCO3. However, adding sulfate ions lowers the permissible concentration factor for calcium sulfate, or SARE.
Ah, another trade-off.
Right. He suggested the most rational approach is to find the acid dose where these two limits become equal. SAD for carbonate equals SOLAS for sulfate. That allows you to maximize water concentration while preventing both types of scale simultaneously.
Finding that operational sweet spot, it really seems Kontsevoy's work provides a comprehensive framework.
It really does. From rethinking the fundamental bicarbonate chemistry, developing that fast experimental test, introducing concepts like admissible pH and temperature, ARNM, TEDM, to applying it all to manage both scale and corrosion in heating networks and cooling systems. It's quite thorough. Plus that crucial point about measuring true hardness.
And the implications seem huge. Better efficiency, longer equipment life, potentially lower chemical and water costs, maybe even enabling zero-discharge systems, and definitely a better way to tackle both scaling and corrosion together.
Absolutely. The potential benefits for industry and municipalities are really significant.
It definitely leaves you thinking. Given how much water quality varies from place to place and how different systems operate, how could these findings be best adapted and rolled out more widely, maybe beyond Ukraine where the research originated?
That's a great question. And perhaps looking forward, especially with the big push for sustainability, what further research could build on this? Could we find even greener, more environmentally friendly ways to achieve the same goals of preventing scale and corrosion in these absolutely critical water systems?
Lots to think about there. It's clear this is a field with ongoing importance.
For sure. And for anyone whose interest is really piqued, digging into Kontsevoy's actual dissertation or related papers would be the next step. There's a lot more detail in there, obviously. It's a great example of tackling complex practical engineering problems with solid science.